Good? Yeah? Okay, we got a lot to get through today, so um, let's try and get to it. Ah, there's Mr. Trapp. Good morning. Huh? That's okay. We'll save the court-martial for next time. All right, so let me go over to, let's see, the Elgato. All right, so last time we were talking trig substitutions, and basically what you want to look for when you choose your substitution is which of these three situations looks most like the problem at hand. So if you have term or terms where there are differences of squares, there's two ways that those could come. Number squared minus variable squared, or the other way, okay? And based on which one it is, you're going to choose one of these two substitutions. Now, the reason that you want to choose one or the other is because number squared minus variable squared should remind you of the trig identity 1 minus sine squared equals cosine squared, right? You take a difference of two squares and turn it into a single thing. The other difference is going to remind you of the trig identity, what's 1 plus tangent squared? You guys remember? Secant squared, right? Okay, so that's going to remind you of that one, and hence secant squared minus 1 is tangent squared. Again, a difference of two squares got collapsed into a single square. That allows you to simplify things, and then hopefully the integral works out from there. Okay, now maybe one other point that I didn't make last time, which is the very bottom case here, where we let x equal sine. Could we have used cosine instead there and have this work out? Yeah, because sine and cosine are mostly interchangeable, right? The one reason that I prefer sine over cosine is, what's the derivative of sine? What's the derivative of cosine? And that minus is annoying. That's the only reason I usually pick sine, but there's no reason you have to, okay? So you could pick cosine instead of sine, and things will basically work out. Just don't forget that negative at the end. Okay. Yeah, because I had to kind of rush through that at the end. So I think honestly at that point, just working out some of these exercises is the best way to kind of get going. And we tried to keep the numbers and stuff relatively manageable with the assignment on Edfinity. So have a crack at those, and then let me know if you've got questions. Okay, so the next thing I want to do is we're going to return to what happens if you're integrating a rational function. Okay, so for example, we saw this, and there was an example where I did polynomial long division on something. This is like a week ago or something. So we're going to return to that sort of situation where I have polynomial on top, polynomial on the bottom, okay? And for sake of a quick example, why don't we just start with the easiest thing I can think of, this, okay? Could we do this one with the trig substitution? Sure, right? In this case, what substitution would you pick? Probably. We got three choices: sine, secant, and tangent. Which one do you think is going to be the droid we're looking for here? Yes, Jack? Okay. What's tangent squared minus 1? Do I know? No. It's secant squared minus 1 is tangent squared. Okay, that one is really easy to mess up. Okay, here's one way to remember which way it goes. That you guys will never forget. Hopefully, right? Divide both sides by cosine squared. Okay, if I divide this by cos squared, and I divide that by cos squared, then I get sine squared over cosine is tangent squared. Cos squared over itself is 1. And then that's that, right? So yes, I used to make this mistake all the time where I had the secant and the tangent flipped. So that's sort of the handy trick. Just think back to the sine squared and cosine squared, and then turn it into the identity you want. If you divided both sides by sine squared instead, then you'd get the cotangent cosecant version of this, by the way. So that certainly works too. Okay, so try again, Jack. Which substitution would you make instead? Okay, and so x would be equal to 1 secant theta, right? So that's the identity that you would use, but the actual substitution would be to say let x equal secant, dx is secant theta, tangent theta, right, and so on. Okay, does it make sense? Okay, so that certainly would work here, and you can go through and do that. What would be a different way that we could approach this problem, though? Yes? Yeah, exactly, right? This is the whole point of the warm-up. Let's break this fraction into two parts and think of 1 over x squared minus 1 as being something over x minus 1 plus something else over x plus 1. The problem is we don't know the somethings, okay? So essentially what we're doing here is if I gave you two fractions and said add them together, what would you do? You'd get a common denominator, you'd go through all the rigmarole, and then bam, you'd end up with an answer, okay? This is doing that process in reverse. Given a final combined fraction, split it up into its constituent pieces so that if you did common denominators, you'd get right back to where you started. Okay. Now the utility of this is once we figure out the question marks, do we know how to integrate one or say a number over x minus 1 or a number over x plus 1? Do we know how to do that? So can I integrate each of these terms, this dude and that dude? Could I do those individually once I know the question marks? Okay. Yeah, and what would the answers be? They would involve logarithms. Yeah? What are the question marks going to be? What kind of thing are they going to be? Probably going to be two numbers. They may not be integers, all right? But they're going to be two numbers of some sort. Okay, so in some sense, for the question of if we wanted to integrate this thing, do I actually need to know what those question marks are? Yes and no, right? The integral isn't going to care because 2 over x minus 1 is going to integrate the same way as 17 over x minus 1. Just be something log of something, right? Okay, but the mystery then is how the heck do we figure out those question marks? A couple ways that we can do it. Well, we just broke Humpty Dumpty, right? Let's put Humpty Dumpty back together again. Okay, so instead of being silly and calling these question marks, let me call them, give them letters. Let's call it A and B, right? So I broke Humpty Dumpty, the original fraction, into these two pieces. Let's put it back together. Okay, how would I put it back together? Well, what's the common denominator going to be? It'd be that, right? And I'll just leave it in factored form. What about the numerator? Well, I would need A times x plus 1 and B times x minus 1. So pause for a moment and convince yourself that that's correct. Okay, Mr. Borden, why is that correct? Right. Okay, so what would you have to multiply a over x minus 1 by to get the common denominator? You'd have to multiply the top and the bottom by x plus 1. And then x minus 1 for the green term. Yeah? Okay. And so that's what it would be when you put it all together. Okay, are we good? Yeah? Okay, so now that I've put it all together, let's concentrate on the numerators. Okay, so let me pick some different colors here. Let's pick red for this guy, and how about, well, no, that's too similar. How about purple for this guy? Okay, if these two things are equal, under what circumstances are two fractions equal to one another? The numerators have to be the same, and the denominators have to be the same. Do we have the same denominators here? Oh, yes and no, right? They don't look the same, do they, Ethan? But they are the same because, right, they're just both x squared minus 1. Because math, yes, exactly. Okay, so the denominators of those two dudes are the same. Sorry, let me be clear when I say the denominators. I've got the red fraction, 1 over x squared minus 1, and then the purple one, that's stuff over the x minus 1, x plus 1. Those two, the red and the purple fractions, have the same denominator. And therefore, if these two things are to be equal, then the red quantity, 1, must be equal to the purple quantity, that stuff. Okay, is that okay? Okay, so what that means is that 1 must equal this. Okay? Can I take that equation, and particularly the term on the right, and go through and simplify a little bit, or rather expand it? Okay, how would that expand? Well, I would end up with ax plus a plus bx minus b, and then I'm going to choose to group things in the following way. I choose to put the x's together and the other stuff together. Okay, so essentially all I did was just collect like terms, right? If I had a 7x and a 3x, I'd put those together as 10x. It's just here I've got a and b instead of specific numbers. Okay, is that all right? Good? How else do I write 1? I'm going to be really coy here, and let me write 1 as 0x plus 1. Same thing, right? It's still just 1. I haven't done anything. Okay, why was that a good idea to write it as 0x plus 1? Yes, Jack? Yeah, exactly. If these two things are equal, then the number of x's on the right-hand side had better be equal to the number of x's on the left-hand side. And similar for the constants, right? Okay, so Mr. Borden, if there are 0 x's on the left, how many x's are on the right? I see an x. What's the number out front of it? Oh, no. It's a plus b. So there are a plus b x's over here, and 0 of them over here. Right? So what does that mean a plus b has to be equal? Right? There's got to be the same number on both sides. So whatever a plus b is had better be 0. Okay, is that all right? Similarly, Ethan, left. 1. Donovan, how many constants are on the right? Right. There are a minus b is our total amount of constant on the right-hand side. So whatever a minus b is, it has to equal 1. Okay, so now this takes us back to high school, or maybe even middle school, or maybe even elementary school for our Korean and Chinese friends, right? When did you learn trigonometry? Yeah. This is the same thing he told me yesterday in the office. So, yeah. Okay, great. So, we've got those two equations. How do we solve a system of linear equations? In this case, it happens to be in two variables. How do we do that? Yes.
Generally, make one that will subtract my cancel out the other, only something from the other variable.
Right. Okay. You could do the elimination method, which is solve one equation for one variable in terms of the other, plug it into the other equation. Although in this case, what's really convenient looking, the b and the minus b, right? What would happen if I added these two equations together? The b's would cancel, and I would get 2a equals 1. Therefore, a equals 1/2, which is not an integer, is it, Mr. Trapp? Well, probably. Only because you said it, and I can give you a hard time. Okay, so that means that a would have to be 1/2. Do we buy that? All right, well, how do we find b then, now that we know a? There's two ways to do that. Which equation do you want to use, Jack? Yeah, exactly. Just it doesn't matter which equation you use at this point, right? So let's just use the top one. I know that 0 equals a plus b, and that means that whatever a is and whatever b are, they're negatives of each other. And so in this case, b would be negative 1/2. Okay. It's coincidence in this particular example that they came out to be negatives of each other. That doesn't always happen, but it did here. Okay. Okay, good. There is a trick for these. Let me show it to you, actually, because it's kind of handy. Hmm? Yeah, yeah. Okay, so let me take this and write it as 1 over that. This trick only works if you have distinct linear factors as the way it factors in the bottom. Okay. So take 1 over x minus 1 x plus 1, right? What are the two values that x cannot be? 1 and minus 1, right? Because then we'd have a 0 in the denominator. Okay. If x equals 1, then this term, the x minus 1, is the problem. So just pretend it's not there. What's the bad value for the term that I just pretended wasn't there? 1. Plug it into what's left. What do you get? 1/2. Right? Okay. Well, let's do it the other way. What's the bad value for x plus 1? Okay, cover him up. What happens if I plug minus 1 into what's left? I get 1 over minus 2, or negative 1/2. Bam. There's my constants. Okay. That, like I said, that trick doesn't always work, but it certainly worked here. We ended up getting the same values. Okay, so if I had 1 over x squared minus 1, we just deduced that this was equal to 1/2 x minus 1 plus, well, minus, but like so. Okay, Gucci? And I'm going to switch over to Twitch here because if I could spell Twitch this morning, just to make sure that I don't have any questions in the chat. Yeah, okay, so those of you guys who are online, if you've typed a question in the chat, I haven't actually seen it, so you're going to have to retype it. Yeah, sorry about that. Okay, so obviously what are we here to do? We're here to integrate, right? So if I've figured out this result algebraically, then that means that if I wanted to do this problem, sorry, then that's the same as doing, fraction. That for the purposes of integration, I've taken a more complicated thing and broken it into two easier pieces. I'll integrate each piece and then we'll put the answer back together. Okay, so that's the purpose of this method is if you start with, if your integrand, the thing you're integrating is some nasty looking fraction, break it up as much as possible. The idea being that hopefully each piece by itself is not too horrible to integrate, but the sum total of it is horrible. Okay, so again, just to recap, what would be the integrals of each of the terms here? The first integral would be 1/2 something du over u okay, and then for the clutch, this one would be that. Yes? Yeah. How else could I write that, by the way, Mr. Trapp? Yeah. I could also write it like this, because what's one of the rules of logarithms? The log of a fraction is the difference of the logs. Okay. And I'm kind of, like I said, I usually always will write the absolute value, but we won't penalize you if you don't write it most of the time. Edfinity might be a little picky. If it is, just don't worry about it, right? Yeah. Okay, so does this kind of make sense? The whole goal is do some algebraic prep work to break your fraction into easier pieces and then just deal with each piece individually. Okay, so maybe another way to sort of analogize this is I don't personally like to wear hooded sweatshirts, but how many of you guys like hoodies? I mean, Ethan is currently wearing a hoodie. It's a very nice pink hoodie. Okay, but a light pink hoodie like that could get dirty, right? Very easily. So how do you wash your hoodie? You put it in the washer. That presumes that you're also going to add some detergent or a pod, right? Okay, and that's that. If your mother were to wash your hoodie, and let's say it had some grass stains on it, what would your mother do? Yeah, exactly. You'd do that fancy spray stuff and let it sit there for a while. She'd pre-treat it, right? Then she'd put it in the washer. And which one would come out better? Your mom's version of the sweatshirt or yours?
Always my mom.
Exactly. Always your mother's, right? Okay, so in a sense, what we're doing here is we're taking our grass-stained fraction and pre-treating it with a little bit of magic algebra. Okay. This particular example, this was not the only way we could have done the problem, right? We could have done a trig substitution. And that's fine, right? In fact, if anything, my favorite problems are the ones where there's like 5 different methods to do it. It's kind of like when you go to a fancy restaurant. Well, not that anybody's been to many restaurants lately, but if you go to a fancy restaurant and they've got like duck 3 ways, where it's like one of the entrees is that they're going to prepare duck in 3 different techniques of preparation, and you get a little bit of each one, right? That's what this stuff is like. It's just like duck 3 ways. Yeah. Okay. Just a fancy restaurant. Okay. So, Gucci. So let me go on to the next stuff here. Let me just pull up my notes. Right. So that's sort of the idea, is that we want to break up a fraction into constituent pieces, and that the algebra is really the hard part, right? Or rather, the tedious part. It's maybe not hard conceptually, but it is tedious. Okay. Um, okay. So let me actually make a bit of a digression here for a moment. And at first, this digression is not going to seem like it has anything to do with what we're talking about, but I promise it will. Okay, give me a positive integer, not too big, a little bigger. That's prime. Give me a bigger one. Give me one that's not prime and 2 digits.
21.
21. Okay, that's a good number. How can you write 21 in terms of primes, right? Now, Will said 7 times 3. Did you? Oh, sorry.
Yeah.
Well, you got a mask on, you're mumbling. I have ear pods in.
I have water.
AirPods, ear pods, earworms.
Yeah, the online document kid.
Yes,
Not seen
yes. Okay, so point being, we could have written it as 3 times 7 or 7 times 3. Are those different? Well, what do we mean by different or same, right? So what makes them look different? The order. But does that really matter? Well, it's kind of up to us, right? But if we say, you know what, I'm not going to count these as 2 separate factorizations because one of them is really the same as the other, they're just reordered. But the order isn't special. It's the numbers that we see that are important. Okay. So you guys buy that, right? All right. So order we won't consider to matter here for prime factorization. Let's pick a different number. Well, let's pick, say, 42, right, which is just double 21, right? Again, I can factor it into, in this case, it's 2 times 3 times 7, and I'm not going to say, or rather, I'm going to say that any reordering of those prime factors is not really a new factorization. It's just a reordering of what we already had. Okay. And it could be the case, like let's just take, for example, 84, double that you might need some factors repeated. Okay, so like for example, here it's 2 squared times 3 times 7. And so just to be sort of systematic, I'll write these things in that order, meaning the prime factors are sort of increasing and then the exponents are whatever they need to be. Okay. But any reordering of what I just wrote is not substantively different. Okay. Okay. Does this work with every integer? Right? Are there any other ways to write, say, 84 without, well, okay, other than reordering the prime factors? Are there any other ways to write 84 as a product of primes? Okay. I mean, yeah, there are plenty of ways. You could do like 83 plus 1, for example, right? But yeah, sorry, so let me rephrase. Are there any other ways to write 84 as a product of prime numbers other than what we have in front of us reordered? Okay, so I can certainly jumble up what I've already written, right? Just change the order around. Is there any other way to do it besides that? Why not? Well, yes. Okay, there isn't another way to do this, right? This is the fundamental theorem of arithmetic. Which you guys have probably never heard of before. Okay, so up to reordering, there's only one way to do it. Okay. Um, oh yeah. So actually, so Farden typed in the chat. How else could you write 21? Well, you could write it 21 times 1. Except, what is 21 not? It's not prime. Okay. So the basic building blocks for this that I'm going to restrict myself to are only the prime numbers. Okay. And what makes a number prime, by the way, it doesn't mean that it's like USDA certified prime number. Yeah. And 1, right? Yeah, the 1 is sort of a silly one. This does have the consequence, by the way, of 1 is not a prime number. It's not composite either, which means not prime. It's sort of the oddball. Um, and this also means that 2 is the oddest of the primes because it's the only prime that's not odd. Yeah. Huh? Well, I said it that way deliberately just to be silly, right? But I'm using the word odd there in two different meanings, right? Which is the sign of all good humor is double entendre, right? Because I used odd in the technical sense of meaning a multiple of 2 plus or minus 1, and odd in the sense of strange. Yeah. So okay. All right. Good. So right. So assuming that we don't let reordering constitute a new factorization, then there's only one way to do this for any given integer. How many of you guys ever knew or heard the name of this theorem before? Yeah? Okay, well, where did you guys hear this? Yeah, number file. Okay. What about you? Oh, yeah. He heard it from me. Okay, well, that explains it. So, okay. Now, the reason why I mention the fundamental theorem of arithmetic is not because we're sitting around here in the business of factoring numbers. What are we sitting around here in the business of? Factoring polynomials, right? Because if a polynomial is the denominator of some fraction, in order for us to do this partial fraction business, we need to factor the thing. Okay, so what this means is we need to think about, well, how do polynomials factor? And as it turns out, they factor basically the same way that numbers do, which is really cool. Okay, so so let me just take, by sake of example, x squared plus 1. Does that factor? Okay, so let me actually write some English here. Does x squared plus 1 factor? Okay, Coy, I suppose I'm not shocked there. Coy says his high school did mention the fundamental theorem of arithmetic, um, but, which means that you two probably learned it in like 5th grade or something, right? So, yeah, American education is not what it is in the rest of the world. We do some things pretty well, but not plenty of other things. Um, does x squared plus 1 factor? Depends on what you mean by factor, but yeah, go ahead, Jack. Not without imaginary numbers is the key phrase. Okay, so yes and no are the answers, right? No, unless we use our friendly number I, the square root of -1. Okay, so it would factor as x minus I times x plus I. Okay, but no imaginaries. Okay, maybe we'll mention them later on, but um, okay. Point being, if you use imaginary numbers, you can factor x squared plus 1 into x minus I and x plus I. Okay. If you do not allow yourself the use of imaginary numbers, then x squared plus 1 can't break up any further. Okay. And what I'm going to call a term like that can't break up, is, so I'm going to call x squared plus 1 an irreducible quadratic. Okay. So an irreducible quadratic would be any quadratic polynomial who has imaginary roots. Okay, x squared plus 1 is sort of the easiest example of that. Okay. Um, I also could have monomials of the form like this. Okay, so x minus some number or x plus some number. Okay, so that brings us to the fundamental theorem of algebra, which is that every polynomial can be uniquely factored into a product of okay over the real numbers. So meaning I'm not allowed to use imaginaries. If I use imaginaries, then I can do a little bit better. Okay, so what this means is that the analog of prime numbers from the prime factorization of integers come in two flavors. They either come in monomials or they come as irreducible quadratics, but those are our prime polynomials, if you will. Okay, things of that flavor. If you allow yourself to use complex numbers, then the statement would be everything can be uniquely factored into a product of monomials, and that's it. But you might have to use imaginary numbers in the process. So if we exclude the imaginaries, then that introduces the irreducible quadratics. Okay. Um, okay, and then do you guys remember the symbol for all real numbers is the R with the extra little bar behind it? That's what I've written there. So when I say factored over R, I mean that I'm not allowing myself to use anything except real numbers. Okay, so I can't use imaginaries. Okay, so notice that the fundamental theorem of algebra and the fundamental theorem of arithmetic are essentially saying the same thing, right? It's just one's talking about numbers and the other's talking about polynomials, but they work inherently similarly, which is really neat. Okay, now, how many of you guys are future math majors? I know Jack is. Yes, they're 1, 2. You're gonna be a math major, right? Yeah, okay, that's fine. Ethan? Oh, financial econ, okay. That's all right. Well, those of you who are going to be math majors, this is an amuse-bouche. That means a mouth amusement. It's like a thing before an appetizer, okay, at a fancy restaurant. And for some of the stuff that you would learn about in abstract algebra or subsequent, advanced abstract algebra or number theory. Okay, so think of this part as a preview of coming attractions. Okay. Now, what's interesting though is the first time I finally saw a proof of the fundamental theorem of algebra was in graduate school, because it involves calculus with complex numbers, and some pretty deep stuff at that. And it was sort of like, finally. Okay. Anyway, okay. So what that is useful for is, let's say, for example, we have an integral problem of the following form. Okay, so let's say that we had this. Okay, and in this case, I'm going to give you in many of the examples we'll actually give the denominator already factored for you, because it turns out that factoring polynomials is relatively hard, in the same way that factoring large integers is hard. In fact, factoring integers is so hard that this is why it's safe to use your credit card on the internet. Okay, or let me be more precise. Factoring very, very large integers is hard, like thousands of digits, right? That's hard. Factoring, 3 or 4 digit numbers is not too hard, but you don't use 3 or 4 digit numbers in encryption. You use things that are thousands of digits long. Okay. So, all right, in this case, we have the polynomial already factored for us, so that's great. So if I were to split this fraction up into 2 pieces, then it's going to be something over x squared plus 1 and something else over x minus 1. Okay, and we'll figure out what the somethings are. That's sort of the task. But before we can figure out what the numerators of these two fractions are, we need to at least figure out what kind of form would they be. Okay, so let's start with the x minus 1 term. What do we expect to see in the numerator for that? What kind of object would we have? Yes? Just a constant. Okay. What about over the x squared plus 1? What might you expect to see there? It's a little bit harder question. Back? Okay, a polynomial of a first degree, or a linear thing, right? So, for example, it could look something like this: bx plus c. Okay. Now, it might turn out that either b or c is 0. Might turn out that, well, it won't turn out that both of them are 0. That shouldn't happen. If that happens, then you've messed something up. Okay. Right. So the way you look at this is you basically put 1 degree smaller than whatever you have in the denominator. Okay, 1 degree smaller of a linear term is a constant, and 1 degree smaller than a quadratic term is a linear term. And you'll never have to use anything other than linear or constant as the numerators, which is nice. Okay, that's sort of another consequence of the theorem. Okay, but here the algebra to find A, B, and C would be a little bit messier than what we had a minute ago, except it's just kind of going to be more of the same, right? So we just broke Humpty Dumpty up, put them back together. Okay, so, and actually, I suppose I shouldn't assume that everybody knows what Humpty Dumpty is. Um, have you ever heard of Humpty Dumpty? No? Okay. You know, it's a children's rhyme, or at least it's probably an American and British one, right? Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All of the king's horses and all of the king's men couldn't put Humpty Dumpty back together again. Humpty Dumpty was an egg, right? Um, why you would need horses to put egg back together is beyond me, but whatever. Okay, so yes. So point being, we just took this fraction, we broke it apart, let's put it back together, and then go through the same kind of game we did a minute ago to figure out what the constants A, B, and C must be. Okay, and so to do that, I would need a bx plus c, and I don't need equal there. I would need bx plus c times x minus 1 plus a times x squared plus 1, and that would equal 1. Okay, so how did I get all of that? Well, what do I need to multiply the first fraction by to get the common denominator? I would need to multiply it by x minus 1 on top and x minus 1 also in the bottom. Yes? And then the second term, I would have to multiply by x squared plus 1 in the top and bottom. And that, what I've written on the left there, would be the numerators put together. Is that good? Okay. What about the numerator of the original fraction before I broke anything up? It's basically just 1, right? Yeah? Okay. So now I have an equation kind of like what we had before. So let's distribute and FOIL everything out and collect the like terms. How many x squareds are there going to be? We're going to have some number of x squareds, some number of x's, and some number of constants. How many x squareds would there be when you multiply everything out? Well, there's going to be a of them from right there. Yeah. How many are you going to get from this guy? B x squared. Yeah? Yes? Okay, so there's B of them there and A of them there. And so how much do we have total? We have A plus B. Oh, Farden, I had no idea that it actually had to do with something. That's perhaps not surprising. So Farden says it has something to do with the English Civil War, I think, and a cannon that was named Humpty Dumpty. So yes, we'll have to do some research into the history of Humpty Dumpty. Um, okay, so that we've got A plus B x squareds. How many x's do we have? Well, here we have to be a little careful. Do we have any x's from the second term, a times x squared plus 1? Are there any from here? No. Okay, great. What about the first term? Well, I'm going to have bx with a negative and cx with a positive. So there would be a total of how many? C minus b. Okay? And then finally, how many constants do we have? Well, I get plus a from the second term, and then the first part is going to give me how many? Minus c. So I'll have a minus c. Okay, so that's my equation, but I'm going to split this into 3 equations because on the right-hand side, where the 1 is, I have a 1. How many x's are over on the right-hand side? There's none. Okay, how many x squareds? Also none. Okay, so what this means is that a plus b equals 0, c minus b equals 0, and a minus c equals 1. Okay, so now we've got 3 variables and 3 equations. Well, that's fun. Yeah. Okay, so what does it turn out here? Well, what does the first equation tell me? A and b are negatives of each other. Second equation tells me that b and c are the same. Okay, and the third equation tells me that a minus c equals 1. All right, so could we go through and solve for a, b, and c there? Yeah, might take a minute, but you guys can do that. Okay, we're over time, so I will cut the stream here. Maybe why don't you guys do this? Try and find A, B, and C there, and we'll talk about it at the very beginning next time, just to make sure that we all got it. And then there's one other thing I need to talk about with the respect to this, which is repeated factors, how to deal with those. We'll also do that at the very, very beginning next time. Okay. All right. Well, talk to you guys later and do some research about Humpty Dumpty. See you later. Don't forget to like and subscribe.